So, hello everybody. Now we will start International Online Scientific Conference, Microplastic and Nanoparticles, Emerging Threats to Environmental Health. And this conference is organized by Faculty of Health Sciences and the Marine Research Institute at Klaipėda University as a part of the project Atmospheric-riverine flux transport and impact of microplastic and microrubbers and as heavy metals vectors on the Curonian Lagoon. And we want to acknowledge for Lithuanian Research Council for this opportunity to organize this conference. And now we will have the first presentation. Associate Professor Dr. Sajjad Abbasi is the head of this project, and he will present our project main results. So, dear Sajjad, please share your presentation and prepare speech. And I want just to say some information for listeners and speakers because we will give you certificates for participation in this conference. So please check your name and surnames. So thank you and have a good time for listening, discussion, and getting knowledge. So, dear Sajjad, please start.
Hello, everyone. Thank you for giving me your time. As you know, I want to talk about atmospheric and riverine flux transport and also impact of microplastics and microrubbers as heavy metal vectors. As you know, microplastic can travel long distance across the continents and also oceans through the air. So sometimes just a few days or a few weeks. In contrast, transport by water is much slower and may take several months or several years. So it's very important to consider the atmosphere as the main way for transport of microplastics. However, it's important to note that these particles can be repeatedly deposited and also resuspended again and again. So because of this reason, we have different type of movement for microplastics in the atmosphere and also on the top of a terrestrial area and also ocean area or seawater, lagoons, and any other places. We had a project, teamwork project 2 or 3 years ago that this paper was published on that time. As you can see here, we have a blue and orange boxes that show the available and unavailable data regarding the different type of movement or flux of microplastics on terrestrial area and also on water area like oceans and seawater. So here we try to show a different type of flux, and but however you can see, for example, orange boxes. On that time, we don't have any information about this type of fluxes. However, these times I expected we have all of this data because we have a lot of research that you can see that a lot of published paper that other researchers and also we try to estimate this type of fluxes. So in the current presentation, I try to have a general and also more comprehensive presentation of some of our project, including Curonian Lagoon. It means I'm trying to speak generally about the fluxes and also include the results of Curonian Lagoon. As you know, the Curonian Lagoon basin span more than 100,000 square kilometer. So receiving contribution from Lithuania, Belarus, and also a small portion from Russia and also Poland. In general, to estimate flux of microplastics in the lagoon or any coastal area, microplastics should be determined in the air as suspended microplastics and also deposited microplastic as a vertical fluxes. And also we tried in some of our project, we try to estimate horizontal flux of microplastics. And also it's important we have a concentration of microplastics in water, in sediment, and also sea surface microlayer of microplastics. In fact, recently we tried to collect microplastics in the thin layer of on the top of the water. In fact, a microlayer of seawater or lagoon water or any place. So, however, in the Curonian Lagoon, we couldn't get SML. When I say SML, I mean seawater microlayer or water microlayer. But in the Curonian Lagoon, we couldn't get it. But in other projects, like, for example, Chorahor Lagoon or Persian Gulf, as a part of this project, we could get this microlayer. I mean SML that I would like to speak about. Our general sampling strategy was to collect samples for 3 different days. In winter and also 3 days in winter, 3 days in summer. So each 3 day include 1 calm day, 1 moderate day, and also 1 stormy day. That I suggest you to do like this because we have different type of weather and we have different wind speed, different humidity, and other meteorological parameters. This can help us to investigate effect of meteorological parameters on microplastics flux in different compartments, like water, atmosphere, and other compartments. When we are working in a coastal area, it's better we take samples twice a day. You know, in the coastal area, or it's better I say that in almost all of the coastal area, we have 2 type of wind, in fact, onshore and also offshore wind. So it's better we can take 2 set of samples during the day when we have a onshore wind, and at night when we have offshore wind. So we expected when we have a onshore wind, in fact, the wind from the sea to coastal area, we have a outflux of microplastics from the sea. So when we have a influx of when we want to calculate influx of microplastics, we are looking for inshore wind from coastal to seawater. So this strategy help us to calculate, in fact, in and outflux of microplastics. So we have different type of or it's better I say that we have different technique for getting SML or microlayer microplastics that you can see some figure in this slide. For example, in the middle figure, you can see a cylinder. In fact, we try to get. First of all, it's better I say that in each technique we try to get 2 type of samples: 1 for water characterization, for ions, and also for elements measurement and other things. And also the second samples was for microplastic determination. So firstly, and each station, in fact, we try to get samples with a hollow but closed hydrophobic glass cylinder that you can see in the middle figure. So was immersed vertically into the water until the most of the surface was submerged. After slowly retrieving in fact, immersed vertically into the water until most of the surface was submerged. After slowly retrieving the cylinder, and process was repeated for several times that for getting the enough. Sorry, do you have my voice because my voice changed?
Yes, it's audible.
Oh, sorry, because I hear a voice in my headphone. Okay. I told that this repeated for several times, and also finally we have enough water that the water should dripping from the surface of the cylinder, and we collect them in a dust jar in a jar. So the process repeated for several times, and so finally this process in fact repeated for 15 or 100 times until the jar was almost full, and also this was sufficient volume to measure electrical conductivity and major ions and elements, and for microplastics. The second method that you can see the right figure in the slide, the stainless steel sieve with pore size of 38 microlayer was submerged to a depth of about 1 or 2 centimeter before being moved laterally and also drawn up vertically through an undisturbed area of SML. So material captured from the entire of SML was washed into a glass jar also, and the process was repeated for several times. For example, in our study for 8 times for us was enough. And also the third method that you can see the left figure here in the slide, the filter paper was just left on the seawater surface for a second and then removed by a pair of tweezers. In general, we use 2 or 3 filters in each station. And also sometimes to calculate the sea spray of microplastics, we collected sea foam that you can see in the figure. However, you can find sea foam in the coastal area also, but we try to get it in the top of the seawater because we want to find the connection between atmosphere, microlayer, deeper water, and also sea foam. So we collected sea foam and also deeper water, subsurface seawater samples for microplastic determination were collected manually in our study. In fact, a glass bottle was submerged to a depth of about half of meter or 15 centimeter. And also, however, deeper will be better if you can, but in our study we couldn't do it. In the deep of half of meter, the cap was opened, and once the bottle had filled, the cap was tightly secured and the bottle was removed, and the content was passed through a stainless steel with a pore size of 38 micrometer that I told you before. And this process also repeated 19 or 20 times until we collected about 10 liter sea foam and also deeper water had been processed. So and also in our project, we get suspended material on a 1 micrometer pore size and also glass filter by a vacuum pump that you can see in the figure, in the right figure, that we use we use this sampler, and also in the left you can see a type of passive sampler. In fact, we deployed this dust collector for getting the deposited microplastics, in fact, for calculation vertical flux of microplastics. And also the diameter of the funnel galvanized steel container was about 30 centimeter, and also half filled with filtered deionized water to trap microplastics and also prevent resuspension of microplastics after deposition. So, however, in the Curonian Lagoon project, we just got deposited microplastics and also sediment and also water of the river and also lagoon and also Baltic Sea. But we try to get two type of microplastics, I mean suspended and also deposited microplastics in other project because for us was possible. And also in our project, we try to get the naturally aged plastic litter. However, this figure is from another project in Poland, but we have the same project. We try to get aged plastic litter in the near to lagoons and collected, and after some procedure, we extract the heavy metals and also element. So I'm trying to speak about briefly. After sampling, in fact, sample were collected and also for filtration and also extraction and identification of microplastics. The samples transport to laboratory, and we identify the microplastics visually and also with help of microrubbers, and also for ions we use ion chromatography, and also for heavy metals in our study we use ICP-OES. Because of lack of time, I'm trying to speak the results briefly. So if you have a question, I try to answer. In general, the results show that the fibers were the dominant shape of microplastics in all of cases, and the proportion of fine microplastics, I mean lower than 100 micrometer, was greatest in the lower atmosphere. I mean, we have a top atmosphere and also lower atmosphere. I mean, I'm speaking about lower atmosphere, while the proportion of large microplastics, I mean larger than 1,000 micrometer of microplastics, was the highest in deposited microplastic or deposited samples, and also in seawater and also sediment. That this result is clear because the denser microplastics and bigger microplastics can deposit it fastly or quickly. And here you can see the polymeric composition of some selected microplastics from different type of samples in Curonian Lagoon that summarize here. You can see the denser microplastics are dominant in the sediment and also lighter in the water, because density, because of a lower density or lighter density, have a so will be lighter than the water density, so it can be on the top of the water. Here you can see some ratio of major ions that exemplified in the figures that you can see here. In fact, the results reveal that a little or no fractionation between almost all ions across all samples types, and also in both seasons, and show a strong marine influence throughout. So it's mean the marine sea spray can affect on all of our samples. However, the calcium ratio involving calcium exhibited considerable dispersion. So with relatively more of the bivalve cation in summer than in winter, and considerable heterogeneity among the deposited samples. You know, I am speaking about the general project. For example, this is from a Persian Gulf project that, you know, all of this is connected to the Curonian Lagoon or flux project that I'm speaking about. In the Curonian Lagoon, also another project in Poland, the results have shown that metal or heterogeneity distribute among the naturally aged plastic litter. So, and overall, chrome and also iron are the less available in plastic litter, and also manganese and also zinc were the most available in our results. Here you can see a general discussion that we try to calculate the different type of flux in our project. The distribution of microplastics between water and also lower atmosphere can be quantified. Term of the dimensionless water air portion, constant akin to that defining the Henry law that I think you know about it. Henry law is using for soluble gases that we're trying to use it in our project because finer microplastics, I mean lower than 100 microplastics, behavior like the gases that you know in some of other modeling, for example, flex part, we used CO2, for example, a type of gas for modeling for estimation of movement of microplastics in the world. So we also use the Henry law in our project. That you can see some other formula here. I can say that briefly that the results show that the enrichment of microplastics and the macro layer for more than 1,000 times. It's mean we have a lot of microplastics in the macro layer that you can see in the figure. So because of lack of time, I prefer to skip this slide. That you have any question, I try to answer. And also here we try to use flex part modeling for source identification in the Curonian Lagoon. And also we use some simple formula in our project. You know, the problem was that our results for macro layer was different to other project because we have you can find just small samples that they are working on macro layer because we have a different technique, we have a different weather, we have a different meteorological climate, and also different type of microplastics in any region. So you know, it's a little hard to compare our study or other study each together. So it's a big important or uncertainty in the in general macroplastic studies. So in our study also we say that microplastics suspended in the lower atmosphere and also collected in the deposited dust exhibit different signature in terms of size and also shape. So we can calculate the settling velocity of microplastics. However, settling velocity can be calculated based on flex part also. So in the project, we use both of them. And also, generally, I can say that microplastics can move between a different part of coastal environment and also any environment in complex way. So influenced by their shape, size, and also the season, weather, climate, and anything other that you can think about. Their behavior seems to be linked to the natural chemical process, like those affected the calcium, or for example, magnesium in water. And also microplastics may interact with organic matter and also affect the ocean surface properties, but we still don't fully understand how. So more research is needed to find out the impact of microplastics on gas exchange and also aerosol production, like for example, microplastics ejection from the seawater by bubble bursting and also sea spraying. So I think we need a lot of research in future to understand this dynamic of microplastics. And finally, thank you for your attention. And you have any question, I will be happy to answer.
Thank you, Sajid. Maybe some questions from audience. Okay, so no questions. And dear Sajid, thank you again for your nice presentation. And the next presentation we will have from United Kingdom, and Professor Ion Skovan will present about vibrational spectroscopy.
Well, thank you so much for the invitation. It's great to join you. It's early morning here in the UK, but it's really nice to join. I'm going to focus a little bit on an area around the analysis and characterization of microplastics. We've been interested in this for a while. My group basically work across a broad spectrum of material science, but in this case, we have a really interesting, if you like, analytical problem that helps us redefine the ways forward. And in many ways, you know, the interest in microplastics and how it's emerged has caused us to reevaluate a little bit how we approach materials and understand them at different length scales. But of course, some of the driving factors around the challenges with microplastics come from an understanding of the breakdown in the environment, an understanding of distribution, and Sajad talked very nicely about some of those mechanisms and our growing understanding in this way, and of course the toxicology that's associated with this, both at the macro level and also with the particle transport in various organisms, including, of course, humans. Eluting out various different components from these give us both molecular scale and indeed elemental scale. And again, that nice reference to the heavy metal potential of microplastic contamination was a very nice introduction. As I say, our focus really is around analytical chemistry, and once samples have been collected, how does that work for us? And you know, our traditional questions in analytical chemistry come under some scrutiny in this area. What are the qualitative questions that we can ask? I.e., what is the identity of the material? What does it contain? But in this context, you know, how we sequence various different techniques to enable us to understand a little bit more around that elemental, molecular, and indeed materials content, because phase of material is really important here as well. And onto that, and this is where actually an awful lot of the standard analytical challenge sits, is how do we apply some quantitation here? Our traditional homogeneous phase analysis of, you know, numbers of units within a given volume, maybe moles per decimeter cubed, or you know, grams per liter, or things like that, really get challenged in the microplastic area. And so I'm going to talk a little bit about how those challenges are now becoming answered. I guess, and I always say this to my colleagues, analytical chemistry can answer an awful lot of questions, but what are the questions that we're asking? And I guess in this area we can boil those down to three different parameters, really. The physical identification of the microplastics themselves. We know that they're relatively small unit fractions of relatively large volumes. But once we've separated, how can we identify size, shape, dimensions, characterize around material appearance, surface characterization, etc., giving us a sort of overall physical identification component. Then, of course, the area around the chemical content. What do we have? What polymer types do we have? What formulations might we have within the individual particle? And indeed, whether those particles have remnants of additives or coatings being applied with the polymers, And again, as nicely described earlier on, what are the potential degradation pathways? Because those become really important in the mechanistic understanding of how plastic materials break down in the environment. And then I'm going to talk a little bit around the quantification parameters that we might use here, what those might mean in context. And I think particularly important is particle counts, particle size distributions, and analysis of that nature. So going on from positioning ourselves really where the collection has happened, we have samples isolated usually on sieve or filter bed type substrates. How can we identify the positions of the particles in that space, and then go through that physical description as well? And of course, we are looking at the microscale. When we get to nanoscale, that's rather more of a research frontier. But working at the microscale is something that's actually well established now, and becoming part of emerging protocols for legal purposes. And so with optical microscopy, we can resolve down to the micro scale, 10 to the -6 of a meter. And as you can see from these examples here, there's a few approaches. Bright field imaging, and using our eyesight to identify specific particles on the bed is one way of doing that. Using fluorescence microscopy, also important. Many polymers will have additives that fluoresce and allow them to be distinguished from the background themselves. And of course, staining processes, again, utilizing fluorescence imaging, also becomes part of that arsenal of activity. Coupled with this, we also now have very easily available image processing software, so we can use contrast and refractive index differentiation to be able to identify individual particles, and of course using computer algorithms work out their size, shape, dimensions, and arrive at those distributions, those quantifications that we talked about. Much of our work, of course, is around the chemical identification, and we use an awful lot of vibrational spectroscopy. And I'm just going to provide a little bit of background to that. Jumped on too quickly. As we know, molecules have unique sets of vibrations, unique energy levels. And at the microscopic level, what that means is that we can differentiate between molecular species based on this vibrational signature that they demonstrate. Now, I gave you a real simple example with water, and as we can see, the two stretching modes and the bending modes of the movements of the hydrogen versus the oxygen give us a very distinctive set of vibrations in the gas phase. When they condense down into the liquid phase, that environment smears out some of those characteristics. But nonetheless, we can identify provide a molecular identification from that. Now, moving systems between different energy levels, we use infrared and Raman to do that. Infrared is a basic absorption process, Raman is a scattering process. And from there, this unique chemical signature, we can either assign ab initio, or indeed can compare this signature with a database. This works very well for pure materials. We need to have some fairly sophisticated strategies once we have mixtures of materials. But remembering we're challenging space volumes here, and one of the beautiful advantages of vibrational spectroscopy is we can focus the light source, either infrared or UV visible and near infrared, into a resolved space. Now, this does have its limitations. Of course, we have the classical limitations of resolution based on wavelength. So clearly, infrared with the longer wavelength has less spatial resolution than Raman that would be using shorter wavelengths. But nonetheless, we can resolve different areas in space and, of course, identify hit percentages and create imaging type views that we see on this particular 2D representation. We can go into third dimension as well, but that's important. Now, Raman and infrared often talked about in terms of providing complementary information, and in terms of identification of functional groups within molecules, we have two distinct mechanisms in this space. So we have stronger responses for polar functions with infrared, and stronger responses for apolar environments with Raman. As a consequence, we have slightly different characteristics within our spectrum, particularly the response, the transition between the vibrational energy levels. But of course, on the x-axis, we have a consistent set of energy differences between the vibrational energies that give us that characteristic signature. Now, this is a little example with a polyamide, nylon type material, showing how the polar amide functions, vibrational modes, give strong responses in the infrared, whereas the apolar, say amide 3 or indeed carbon-carbon stretching modes, gives relatively strong responses in the Raman. Now, that's all well and good. We have a signature that we can compare to database and whatever, but of course, the situation is complicated because polymers aren't usually pure, plastic products aren't usually pure polymers. And there's a nice little showing here of polypropylene spectra, showing that not only do you get the prime material vibrational signature, but you also will get additives in certain circumstances. So that's an important concept to think about when we're assigning, identifying, and if you like, qualifying hit levels against database in that space. Of course, also important is degradation processes. Again, we can look at specific vibrational signatures that will indicate some of this degradation. So not only can we identify the material, we can also potentially understand the degradation processes that are going on with that material, and indeed feed that into a more mechanistic understanding of what's going on. So I'll just conclude with a last little slide, which talks to one of the projects I've been delighted to get involved with my friend Rashidi, and indeed Reda and other colleagues, where we're going to do some microplastic characterization in Tioman Island in Malaysia. I'm looking forward to doing this. And I've just talked about, within this slide, a little workflow which is around that characterization phase, deliberately starting at 0.4 because there's all a collection separation process to go on before that. But in terms of physical characteristics, using microscopy with automated imaging will provide us with outputs such as size distribution morphologies and a classification around color and if you like, origin. So we can infer that from the physical characteristics. With chemical identification, access to both micro Raman and FTIR. FTIR for larger particles, Raman for smaller particles, each of which, and I don't have time to talk about it today, have their limitations. We have some challenges, of course, with particularly fluorescent additives in Raman spectroscopy, as an example. We can also interpret those results in terms of degradation processes, oxidation processes, etc., and start to feed that into an understanding of how the environment and the environmental stresses are causing that polymer degradation. And lastly, bringing these things together, attempting some approaches around the quantification, particularly with particle counting, particle size distribution, particle shape distribution. So that's our proposed workflow moving forward. Very happy to answer questions, and thank you all for your attention, and in particular, thank you very much for your kind invitation to share some of my thoughts around the challenges that modern characterization methods provide us with. Okay.
Professor Ryan Scoven, it is really nice to see you again, and your knowledge about microplastics will help us to collaborate in future research. And maybe some questions we have. Of course, we will have at the end of conference discussion about sampling. Maybe we will go deep in details. So thank you again for your presentation. And now we have our colleague from Malaysia. Next presentation will have Rashidi. I know he is here, and I want just to introduce Rashidi. He is very active in collaboration between different scientific groups, and now he organized a big scientific research project about microplastic sampling in Malaysia. And maybe some information we will get.
So without further ado, I'm going to display my works based on the project that I would like to mention in less than maybe 10 minutes. So my topic is on microplastic sampling and characterization in beach sediment. So we would like to show two areas of interest. One is in Southeast Asia, and also the last one will be in Sweden, since I'm in Sweden at this moment. So I'm working at the Department of Chemistry, University Putra, Malaysia in Kuala Lumpur, but currently I'm doing my sabbatical at Lund University in Sweden. And if you look on these presentations, I would like to mention that this is just a fact that in South Asia, plastic waste is an issue where they were dumped into the ocean. And based on the 2015 report, we know that there's a large numbers of 8 million tons of waste of plastic going to the ocean, and Malaysia is one of the known countries to have waste on plastics. And what we did last time, we went to several beaches in South Asia, namely as Tioman Island. You have seen just now where we were. And we also went to Bali, Indonesia, as well to Banda Aceh. But we will not discuss in this presentation. And the last one, we were in Yastad Beach in Sweden this year. So what we found out, these are the sampling sites. As you can see, the top one is Bali. So we cover several areas of Bali beaches, as well in Tioman area. So it's a wonderful tropical region, as well with the cold environment in Europe. Okay, so yeah, so this area are on the beach sides of every single countries that we selected. So what we normally do is the same protocol, we will go for samplings. We will do sieving. That's our strength on the separation of sizes. And after that, we will try to split the sample into density separation. So the less denser and the higher density will be split easily. And of course, we only have limited technology on the optical microscopy, but we did some good work on infrared, such as ATR, Raman, and also OPTIR recently. And we have limitations in terms of sizes. Of course, we will like to exclude anything that larger than 5 millimeter, but our smaller sieve is 212 micron meter. And we also, during the field sampling, we do not have, we normally do in situ density separation, basically by filtering the seawater, and we can get density separation experiment. And finally, we also do sorting in situ measurement as well with the help of our highs. But when it comes to the lab, we can get the images of the sample, and we also measure the density of the seawater in Asia. So that's the value of the density of the experimental data is around 1.02 gram over cubic. So we know that we are using the right concentration, density of material for the purpose of separations. This is in general. We did some collections. We split them first on the first protocol on the separation on density, and then we will do the sieving. And after that, we can get different fraction of sizes based on the different sizes of sieve. So we can have large for over 5 millimeter, mediums, and small according to the size. But normally we still can get the small size, even to the fraction of small, according to the sizes of that we have. So this is one of the fieldworks example. It's a beautiful island. We can see yes, huge pile of samples sometimes, but of course we will not collect them because we have the right protocol. And this is work was done with the Japanese team 2 years ago. So in terms of units or quantitative that Scowen's mentioned before this, yeah, in this area we are looking on two types of units. If you are looking on the liquids matrix, the unit very likely in the numbers of particles, numbers of microplastic particle over the filtered water volume. All right. And if we doing it in the sediment, so we have the unit. So how much is that for over the dry weight sample? And in the lab, we also dry the matrix, and we found out this is the sample mass that we use in our dry weight measurement. And what we found out in Southeast Asia, there are several dominant polymer as polystyrene, polypropylene, polyethylene, and also acrylic derivative. And what we found in terms of colors, we found white, green, blue, and yellow. Those are the three major colors. And in terms of shapes, we found fragments, foam, fibers, and pellets in terms of their shapes. And this is like consistent across Tioman and Bali. So maybe some of you may have different setup in the laboratory. So this is what we only have. We only have this optical microscope. So we will collect the particle regardless whether they will be classified as plastic or non-plastic at the end of the projects. But these are very suspicious material that we found during the sampling in South Asia. So yeah, they look like plastic, but at the end we need to perform the chemical characterization. So these are the images. What we found out that using ATR method is effective for larger microplastic. I would say 1 millimeter should be enough, and we very likely can have the identifications. We also use Raman spectroscopy with different type of laser. Of course, we limited to 785 nanometer at this moment, and yes, we expected fluorescent is the challenge. And yeah. And when we move to higher setup on the optical photothermal imaging, we can go to submicron resolution. We very likely can observe degradation or even further chemical composition of the beside the polymers. Okay, but we have not gone into detail onto the deep study of the chemical characterization. This is an example of infrared spectroscopy that we did last time. And as you can see on the red color, we are very lucky in University Putra Malaysia. We cover from 60 to 6,000 wave number for the Bruker in Vino setup. And yeah, if you see there is nothing even on 5,000 over 5,000 signal, but we're still using the whole spectral region to make sure that we know that we're covering the whole spectral region. Of course, the identification will be start on the mid-infrared region. It's sufficient for the polymer characterization. Yeah, this is example of several stacks of OPTR spectra. Of course, we notice that there are some fluctuation of the absorbent. We also have some new formation of peaks in certain regions. You can see on the green color. We have not integrated that in detail. This is one of the particle of the fragmented microplastic that has been identified as polymers before this. But when we look in detail on point to points, we probably know much detail after this. So we also expanded the project with some ideas on to see can we do stacking with comparison with another techniques between infrared, ATR, OPTR, and even Raman, and the last one will be on the computational. So I think computational also work at some point to justify whether we have a pristine molecule of polymer. Yeah, it doesn't count on the contribution of the minor substance, but yeah, that's how it works. We try to see some information that we can get, plus hopefully we can do a precise vibration assignment with the right vibrational mode. And yeah, further up from that point, we also did some work on this imaging, and we use another way how we try to tackle on the rule-based color labeling. So this is using computer technology, and we would love to use the technology to give to assign colors of substance. So this is in another work by the Faculty of Science Computer people in University Putra Malaysia. They developed this methodology to the assignment of colors, and on the last part of the project, we also extended the project on the GIS analysis. So we use remote sensing to map the microplastic transport pathway. So this particular in Bali cases, and they have some finding that we have not published yet. What we should say to other people, yeah, microplastic can be seen across Southeast Asia. This methodology on sieving, density separation, spectroscopy are effective for baseline monitoring. We found polymers in different areas, and what we would love to see in future is we would like to expand this project in the liquid state matrix, where we would like to study microplastic in fresh water, coupled with some technology from different part of the world with their advanced methods, and probably we can go for degradation, because that's also another direction that we should see, because fresh water is relevant to the needs of drinking water. All right. So this is an example how it works on Mersing River, another site of sampling beside the Tioman that Scott mentioned. And this is the boat for the sampling. So we're going to use bamboo to make sure that we can tie the plankton net, and we can do trolling across the sampling site. So we are expected to have more than 10 sampling sites, and this can be done in less than 1 day. So I would like also to acknowledge some people around the world, especially from the Malaysia team, from Sweden, from United Kingdom, from Japan, Australia, Germany, Brazil, Chile, Italy, France, and also the United States team who helping us in this particular project. And of course, within this meeting with the European team, we should be able to see more partners in the European region where they also have their own interest on their particular project, which also in parallel with our needs in Southeast Asia. Thank you very much.
Thank you very much, Rashid. And as I understood, we have one question or hands, as I see.
Yeah, I'm willing to accept any questions.
No, I can see a question in the chat. Also, you can write in the chat some questions if you have during presentation. And of course, as I said, we will have a discussion after the end of conference.
Absolutely.
Okay, and thank you again for your nice presentation. And the next presenter we will have also from Malaysia, and Professor Norizak Abdul Rahman will have, as I understood, from analytical point of view, And Norisa, are you ready for presentation?
Yes, yes.
Okay, thank you. And nice to see you again.
Nice
We are collaborating, writing project, discussion, and also I am very happy that you agree to present your experience. Thank you, and please present.
Okay, thank you, Prof. Reda. So basically, I'm Noriza Abdurrahman from the same department as Dr. Rashidi, and basically we are from the same group of doing microplastic from UPM. So what I'm presenting today is actually a small part of the what Dr. Rashidi already explained just now. So this is focusing on the use of ATR, FTIR, and also Raman spectroscopy for the analysis of microplastic that we obtain from Tioman Island. So plastic is very useful, durable, lightweight, but because of durability, it caused some problem to us because of its persistence to the environment, and the degradation of this plastic can go into microplastic, and also now we have a nanoplastic. So this can actually can have some impact to human and also environment. The one that we are focusing today is only the Tioman Island. Tioman Island is located in Malaysia. It's a beautiful island that high biodiversity and also tourists, but it also has a monsoon that actually giving the accumulation of plastic in the island that can cause damage to the environment surrounding it. So for the analysis of the microplastic, for this one we are focusing on the vibrational spectroscopy, which is IR, ATR, FTIR, and also Raman spectroscopy. So these two technique that is known for the non-destructive and preserve the samples, and also provide accurate chemical identification, and also can be applied diverse metrics, including water, sediments, and also environmental samples. So the strength of the ATR, FTIR can actually provide fingerprints of the polymer structure. And the most important thing, especially for those working in Asia, especially in Malaysia, the method need to be accessible and also affordable. Because of the source constraint for us. So FTIR is actually considered as affordable and also accessible. Many of the universities have their own FTIR and also Raman. And second is the high identification accuracy, and also it can work a wide range of particle size. But for ATR, FTIR commonly is for larger size of microplastic. And it also can work in semi and fully automated, where it can actually reduce manual workload and also analysis time. But there are some limitations, such as reliability on the spectral libraries, and also the sample preparation can affect the quality of the spectrum. But these challenges can actually still remain attractive for this method, where it still considered as a cost-effective, user-friendly, and also versatile method. And the second one is the Raman spectrometer, where we use a microscope with the multiple laser excitation up to 1064 nanometer. So it is one of the powerful technique to analyze microplastic. The key advantage where you can actually get the image of the microplastic, and also you can take the image without destroy the samples, and you can actually alter the wavelength that you work on. So you can choose that the wavelength that can reduce fluorescent interference during the measurement. But it has some limitations, such as interference from additive, or because of the samples exposed to the biological and etc. can have some fluorescence on the surface of the microplastic that can actually influence the quality of the spectrum. And for the methods, this is already explained by Dr. Rashidi, where we use sieving and also density for separation. And for this part, I only focus on the ATR, FDR, and also Raman, and some of the images from microscopy. This is the ATR, FDR spectrum of the one of the microplastic that we obtained from the Tioman Island, where the top one is actually the real samples, and at the bottom here is the spectrum we get from the library. As you can see that the very strong peak of CH peak that have a very high confidence level similar to the library, but in the region of 1500 to 750, we have a weak and partially unresolved peak, possibly due to the environmental degradation or surface oxidation, or maybe some inhomogeneity which are known to affect whether microplastic. So the environmental degradation and surface oxidation, possibly due to the exposure of the microplastic to the seawater, and interfere the spectral characteristic. So for this one, we obtained this spectrum is very similar to the polypropylene isotactic spectrum. And the second one, we use a Raman spectrum, where we use a different excitation wavelength, which is 532, 333, and also 785 wavelength laser, that only 532 get a meaningful spectrum, where we can observe several peaks. The first one is around 2900, which is due to the strong CH stretching vibration, and 1091 here is maybe due to CH2 bending vibration, or also symmetric stretching vibration of carbonate ions, and 550 and also 474 indicates of the sulfonate groups that come from mineral phase. So this finding actually pointing out the presence of the identification of microplastic, and also the presence of the carbonate and sulfate inclusion on the microplastic. And this is the images of the microplastic that obtained. Some of them you already seen in the Dr. Rashidi presentation, and the predominant polymers is polystyrene, polypropylene, and also high density polyethylene. And the color is mostly white, about 30%, and the weathering yellow and spectral distortion. And for the comparison for the two spectra obtained for this analysis, actually you can see that ATR FTIR is highly reliable and also accessible for us, especially for larger microplastic, and it can actually give high confidence polymer identification, but has some limitation with triggered spectral for weathered sample. And Raman spectroscopy, on the other hand, theoretically very effective for smaller particles, and also from the spectra we can see that we can see the minerals presence on the microplastic. And but if you compare the three wavelength that we use, only one that works for the microplastic that we test. This is possibly due to the fluorescent interference that actually you have to explore different wavelength for the right for your microplastic. And with that, I would like to thank actually the leader for this project is Dr. Rashidi, and the rest of the collaborators for the work, and also the funding from Grant Putra UPM. With that, thank you so much for your listening and attention.
Thank you so much also, Norizak Abdul Rahman, and I can see questions, but as I said, please, if you have time, please stay until the end of our conference. I know that in Malaysia it is late time, but we will discuss about sampling, about analysis. And thank you again. And the next presentation we will have from Poland, from Torun. Monika Chmielowska is also our postdoc at Klaipėda University. And I see Monica, and now she is preparing to present about some protein supplements and their packaging. So please, Monica, we are waiting your presentation, and nice to see you again. We also have very long cooperation.
Thank you, Reda, for your invitation, for your introduction. So good morning. My name is Monika Chmielowska, and today I will present the results of our study entitled Alternative Plasticizers in Protein Supplements and Their Packaging, Comparative Studies Using GC-MS Technique. This research was conducted in collaboration between Poland and Lithuania. So plasticizers are used to improve the flexibility of plastics, but many of them are endocrine active and potentially toxic, especially in reproductive and developmental contexts. For many alternative plasticizers, toxicological data and regulation are still incomplete. They are still challenging for researchers. In addition, newer alternatives are emerging, and we do not know what their physicochemical and toxicological properties will be. What is more, micro and nanoplastics can serve as carriers transporting these chemicals into food, living organisms, and also into the environment. APS are semi-volatile compounds with diverse structures, branch structures, polar esters groups, long carbon chains, and aromatic rings. DHT has so far been considered as a less toxic substitute for phthalates. However, in vitro and animal studies have shown the potential for endocrine disruption at high exposure levels, as well as possible liver effects. DHA may also act as hepatotoxic at high doses. In the case of DBS and ATAC, there are concerns regarding reproductive effects based on related phthalates, but data for these alternative esters are still insufficient for a full assessment. Protein supplements are widely consumed not only by athletes and active peoples, but also by patients with chronic diseases. That means any contamination of these products can potentially affect vulnerable groups. Our aim was to evaluate the presence of alternative plasticizers in both supplements and their packaging, and to assess potential migration pathways. In our study, we analyzed a selection of commercially available protein supplements packaged in plastic containers. The products were chosen to represent a range of formulations, including protein isolate, concentrate, and protein shake. In short, for the protein supplements samples, an analytical procedure was applied that involved ultrasound-assisted extraction, dispersive solid phase extraction, and classical solid phase extraction. Identification and detection were performed using gas chromatography coupled with tandem mass spectrometry, GC-MS-MS, in multiple reaction monitoring, MRM mode. For the packaging samples, a simplified analytical procedure was applied based on ultrasound-assisted extraction. And this slide presents the working conditions applied for the GC-MS-MS, so the type of chromatographic column, injection volume, and GC-ON program. The parameters applied in the MRM mode, such as collision energies, as well as precursor and product ion transitions, were optimized in advance to ensure the highest possible sensitivity and selectivity of the method. At least two transitions were monitored, namely the main transition and confirmatory transitions. In the table, the main transitions used for quantitative analysis are marked with a capital Q. Data are also provided on deviations between the M to Z values of the main ion and the first confirmatory ion in the calibration solution, compared to those obtained from a spiked sample. A similar comparison of deviations was made for retention times. To ensure quality control of the results, 3 replicates were performed for each sample. Blank samples were also used to eliminate the impact of background of the results. The method showed good accuracy with recovery between 80 and 96%, depending on the sample type, and good repeatability. That confirms the reliability of our results. As shown in the charts, the highest concentration were detected for DHT, nearly 14 nanograms per gram in packaging, and up to 6 nanograms per gram in the protein supplements, which may confirm the potential of migration of this compound. The presence of DIBA and DEHA in the supplements also suggests the possible transfer from the packaging material or raw material contamination. what is interesting, the least volatile compound among those analyzed, trimelitate TOTM, was found at elevated levels in the packaging of product number 1, while its concentration in the packaging of other compounds was much lower. A similar profile was observed in the protein supplement samples. Elevated concentrations appeared only in product number 1. This may confirm the migration of these compounds into the food. Migration can occur via direct contact of the powder with packaging, via aerosols generated during handling, or even via micro and nanoplastics acting as vectors. Factors such as storage temperature, fat content of the product, and residual moisture can accelerate this process. To estimate consumer exposure, we assumed a daily portion of 30 grams of supplement with a body weight of 75 kilograms. Based on those assumptions, we calculated daily intake values and compared them with available toxicological thresholds. In most cases, exposure was well below limits established by EFSA or reported in the literature. In conclusion, alternative plasticizers are indeed present both in protein supplements and their packaging, but at levels that do not currently indicate significant risk. However, the lack of legal regulations and insufficient toxicological data, particularly regarding long-term and combined exposure, remain a challenge. Future studies could focus on migration under realistic storage conditions and the role of micro and nanoplastics, and expanding such analysis to other food groups and packaging types is also necessary. Thank you for your attention.
Thank you, Monica, very much. As usually, you're doing very good presentations, and I also want to invite next presenter from Vilnius and Center of our Physical Sciences and Technology, dear Mehdi Hassan Milu. I'm not sure that I said in right way your name and surname. Sorry for that.
Oh, it's fine.
And
Thank you.
yes, because our project is connected with microplastic and heavy metals, and it is really for us interesting to share knowledge about this absorption effect, because it is very hot topic and a lot of discussions, and it is necessary to observe absorption effect of these particles, because microplastic working as nano carriers particles, if we will look going to nanoparticles effect. So maybe some words about you, from which country you come to Lithuania to do research, because you're working in very strong team, and we are very happy that you agree to participate in our conference. So thank you again for your participation, and it would be interesting to listen your result.
Thank you very much. I am Mehdi Hassan Milu. So basically, I'm currently doing my Erasmus Mundus Joint Masters in University of Technology Prague, Czech Republic, and University of Oviedo, and Our Academy University in Spain. So And it was like very, very great. I mean, exposure that actually I have been here into Lithuania in Vilnius, and I'm currently doing my summer research internship with the team of like environmental science group at the Center for Physical Sciences and Technology in that institute. So actually, it was my work for my last almost 2 months for my research and everything. So I would like to share some of the insights of it. Thank you. Thank you very much. And thanks for the invitation to the International Online Scientific Conference 2025 on microplastic and nanoparticles, which emerging threats to the environmental health. Okay, so today, how can I proceed? So at first, I would like to go to the my topic, which is applications of polyethylene, terephthalate, and polystyrene nanoplastics for adsorption of cobalt and europium. So if I going forward on it, I would like to share some insights about the contents of the review. So on the outline, I have structured about the sources of nanoplastics, how it come in the environment, and how it occurs in the in different kind of structures and everything, and how we prepare the nanoplastics in our laboratory, and how we characterize them in different kind of methods and methodologies. And at the end, I will try to discuss about the adsorption of metals and radionuclides on nanoplastics, like how it affect these nanoplastics even, and how in the conclusion, I will try to summarize a bit. Thank you. So in the next slide, if I going for sources for the nanoplastics in the environment, we can categorize them or differentiate them into 2 categories. So primary sources and secondary sources. So in the nanoproducts scale, so the primary sources are nanoplastics. It basically coming from nanomedicine, nanoimaging, personal care, or even industrial products. For instance, we would say plastic pellets and powders. And on the secondary sources, it basically comes from the fragmentation of huge or larger particles through different kind of weathering, wear, or even from the degradation process. Why it is very important? Because even for we saw different kind of research and about our results about the microplastics, but for nanoplastics, because it differs for its different kind of characteristics due to its tiny size or particles or different kind of features. In the next slide, I can show why nanoplastics. I mean, these are having some toxical effect due to some factors such as some particle size, about their surfactant properties due to their charge or different kind of functional groups, or even they have different kind of cell types. Some common toxic effect that involve with these nanoplastics when it comes from it can actually generate it and it can transport it to our human body or the human vessel, then it can actually create us some oxidative stress, inflammation, some cytotoxicity, and sometimes disruption of cell signaling and metabolism. So that's how it can actually increases the human toxicity, and it actually toxic for the health sometimes as well, and also obviously for the environment. So this is on the preparation and how we actually prepared nanoplastics in our laboratory. So we try to collect some of the ordinary PET bottles or the plastics that are the food containers, that we try to prepare it, and we try to collect those things from, and then we try to categorize them into 2 categories, like how we try to separate them. So we use mechanical method, and we also use the chemical method as well. So on the mechanical fragmentation, we try to use those plastics and we try to grind them in the ball milling process. So in the picture, we can see the ball milling process is here, and with the ball milling, we try to grind all the plastics and make them into a very tiny size, so that we cannot sometimes differentiate at the same time. And then after, we try to go for different kind of processes. For instance, we went for mechanical fragmentation, dispersion, and different kind of purification. And on the nano precipitation, we use different rapid increase system, or sometimes diffusion of different kind of solvents. Sometimes we use trifluoride acetone and different kind of aquatic phase as well. So it leads to the decrease in the solubility for the polymer. And on this nano precipitation, we use dissolution, dispersion, and solvent removal process as well. So basically, we have 3 categories things. So we have polystyrene, we have chemically PET, and we have mechanical PET. So these are the processes that we have used in our preparation on the sampling system. And with the nanoplastics, after the preparation, we try to characterize them. We use ATR-FTIR system, and also we use SEN method. So on the scanning electron method, the morphology and the size distribution of the particles are studied clearly using the same method. So we can see here different kind of polystyrene, and we try to execute it and try to scan them in a electronic microscope, and we found different kind of samples there as well. So this actually clearly indicates that actually sometimes these particles for this kind of nanoplastics can actually involve in other kind of particles. For example, this can be radionuclides. We have used here, of course, cobalt and europium, and it can be other as well. And later, we used to do another FTIR for the CPET and MPET. In the chemical PET and the mechanical PET, we have seen here different kind of pictures as well. But in this picture, they actually make a very good bindings with ether and hydroxyl bond. And these bindings actually can trace and use this kind of nanoplastics and sometimes radionuclides sticking to its surface. So it will not absorb, rather it will adsorb, and it can transport to the various way, in the long way. And it can even transport it into environment, obviously, and from the environment, it can boost to our health. And it can cause different kind of symptoms and different kind of issues in our health disorder. And on the adsorption of the cobalt and europium, on the nanoplastics, we try to use different kind of solution. And for example, we use different kind of diluted method, and there we traced by the europium and cobalt ion. And we have used our pH which is very important in this experiment, because in the adsorption, it is always controlled about the pH because of its surface charge and metal specification. So we have used a low pH where the hydrogen ions compete with different metals, and the absorption was lowering. While we can see in our experiment that while between 6 to 7 or 8, the deprotonated sites while doing the pH balance, it gives actually the best result while doing the experiment in the polystyrene or even in the MPET. So there are some results that I have shown in the graphical figure. And later, if I go to the kinetics, because while we are doing this kind of experiment, we try to figure out some kinetics actually in the first order and second order. So in the first order kinetics, we can see that this europium and cobalt ion, these both are active. So both are really doing the absorption. But on the second order kinetics, we can see that actually it actually absorbs more because it's a very short time and it can actually reach to the equilibrium in a very good stage. So that's why we can see that actually on the due to the first order, the second order actually prefers more to absorb all the kind of ion. And I also try to show a picture about the absorption kinetics of europium ion from the Baltic Sea water with different kind of nanoplastics. For example, PS like polystyrene, MPET, and CPET that we have tried to use here. And on the adsorption isotherm, we have differentiated with Langmuir and Freundlich isotherm. So why we use this kind of isotherm? Because it actually clearly reflects whether it is monolayer surfactant or it is using on multilayer or this kind of physical or chemisorption adsorption. So in the Langmuir isotherm, we can see that on the figure with blue and red, the Langmuir isotherm model data, it actually fits more closer rather than the Freundlich model isotherm data. Because we can see here on the radius of this, all the kind of isotherm, the Langmuir actually prefer better result than the Freundlich isotherm. So with this parameter, we can say that actually this result clearly shown that actually that our nanoplastics, it can actually carries the nuclides or heavy metals with it. And on the conclusion, we can say in a very brief way that actually the PET and PS nanoplastics prepared in different kind of studies we try to absorbing cobalt and europium ions, which are clearly affected or influenced by pH. The adsorption europium ions that I have already said that it actually occurs on the homogeneous sites with the composites of monolayer absorption, on the basic absorption on the Langmuir model rather than Freundlich model. A clear absorption we have used in the second order second order model observed in the europium ion and also ion exchange in the surface complexation. But at the end, there's a clear message that we can say that these nanoplastics actually can play a dual role or a various role. So while they are, of course, as a polluter themselves, and they can also carry the heavy metals or nuclides. For example, we have used cobalt and europium in the environment. and thus it can affect and it can transport to our even for the human body as well, or eventually in the environment. And these are some of the reference. And I would like to acknowledge Research Council of Lithuania with my summer internship and everything regarding this project. And thank you very much for all of you for the attention and everything. And if there is any question, of course, feel free to ask. Thank you.
Thank you very much. It is really, for me, was useful presentation, and I'm so happy that you agreed to present your results, and thank you very much. And also we will have a next presentation. Karina Kuzborskaya will present about radionuclides and nanoplastics, which are both emerging environmental concerns, and their potential interactions are gaining attention in the recent research. And Karina, are you ready?
Yes.
To share your screen? I know that you have a big group from Vilnius, from Lithuania, from State Scientific Research Institute, Nature Research Center, and Center for Physical Sciences and Technology.
So, hello everyone. I hope you can see my slides and hear me very well. Please let me know if sound or video is not clear. So, today I present magnetic hydrogen nanosorbents for adsorption of radionuclides and nanoplastics. So, hydrogen. So hydrogen is a natural biopolymer, well known as its ability to absorb or capture different pollutions from water. On his own, it already shows very good sorption efficiency. And magnetite, an iron oxide material, has also been studied for separation process because it can be controlled by magnetic field. And in our work, we combine these two materials together by adding magnetite into hydrogen. We created magnetic hydrogen nanocomposite, with which easier to separate from water using a simple magnet after the absorption process. So we synthesize magnetite nanoparticles from iron chloride 2 and 3 in a ratio of 1 to 2. Then we prepared several nanocomposites of hydrogen with different modes, materials in two different directions: radionuclides adsorption and nanoplastic adsorption. For radionuclides, we use cobalt-60 and europium 152. And natural water samples were collected from Baltic Sea, Balsis Lake, and Neris River. So there you can see scheme how we do this experiment. In this sample, we add stock solutions of target ions and tracer of radionuclides. The absorption experiment lasted for 24 hours. After this, the magnetic hydrogen particles were successfully separated from the water using a magnet. For nanoplastics, we performed similar experiment, but instead natural water, we used this distilled water because we started this experiment not yet. And characterization. To study the structures of materials, we used scanning and transmission electron microscopy. So there you can see hydrogen. Pure hydrogen showed a smooth surface, while magnetic hydrogen composites were rougher. Yes, this is one showing the magnetic particles attached to the surface. We also used the XRD and TIR. And another important property was the hyperfine field distribution, where we could clearly see difference between pure magnetic and our nanocomposite. So I have video. 1 second. I have also video demonstrated showing how the particles become magnetic separate from solution. And results, the removal efficiency of composite with 30% magnetic, we call MCN30. So for cobalt-2 in nearest water, the removal efficiency was about 37%. And better results of European was in Balsis Lake, 114 milligrams. Oh, sorry, European free in Balsis, it's reached 80%. And we calculate sorption capacities were also high. So cobalt-2 up to 11 milligrams per gram in Baltic Sea, and europium-3 up to 114 milligrams per gram in Balsis Lake. And this means that material works better in water with lower salinity. The absorption is a term analysis using Langmuir and Freundlich methods showed that absorption happens both by hemisorption in a single layer and physisorption in multiple layers. And now about nanoplastics. So we also carried out pilot studies with nanoplastic for polystyrene nanoplastic. MCN30 showed very high adsorption, about 99% efficiency calculated using two different adsorption models. And we have other plastics, so it's a PET. For nanoplastic, we observed that adsorption was better with MCN10. We composed with more hydrogen and less magnetic. So this, and I will not repeat all conclusions in details, but to summarize, the synthesis magnetic hydrogen nanocomposite demonstrated good structure properties and strong magnetic separation ability. The composite showed promising performance in radionuclides removal. For nanoplastic, the removal efficiency was even better. And thank you for your attention.
Thank you, Karina, for your nice presentation and magic video. So I see in the conference chat we have a small discussion. I am pleased to other listeners to be active in chat if you have questions. And now I want to invite Aida Bradauskaitė. Aida Bradauskaitė finished Klaipėda University bachelor studies, and Aida was my students. And Aida, are you listening to me?
Yes.
Yes, okay. And later, she continued studies at Konexus University, and she has future plans to going more in science. And Ida, please introduce yourself about your experience, because I know you have international collaboration in Germany, in Spain, in France. So maybe you can introduce a little bit about yourself.
Yes, so a year ago, I also finished Erasmus Mundus joint master program in marine biotechnology. During these 2 years, I studied in Spain, France, and Germany. So in Germany, at the Max Planck Institute, I did my master thesis topic in planarian immunology. And now I am again in Lithuania and planning to start my PhD in Vilnius in Nature Research Center. So I will be also working in this topic related to microplastics and pharmaceuticals. So it's really a great opportunity for me to be in this conference. And I wanted to ask if you can see my slides, my presentation.
Yes, we can see.
Okay, then I can start. So I will present the topic of fish as a model system for environmental health studies on microplastic and pharmaceutical interactions. So in our study, we focused on one particular drug, which is hydroxychloroquine, HCQ. It is an antimalarial drug with immunomodulatory, antibacterial, and antiviral properties. HCQ was widely prescribed for COVID-19 treatment, leading to an increase of its consumption during the pandemic. However, little is known about the ecotoxicity of HCQ in aquatic environments and its interaction with nano and microplastics. So we aim to evaluate the potential effects of HCQ both alone and in combination with carboxylate modified polyestyrene-based nanoparticles, the PS, on the well-being of Salmotruta embryos and larvae. And the experiments were performed on egg stage embryos and early stage larvae of Salmotruta. We evaluated their survival, heart rate, and gill ventilation frequency. The test groups included the control group, the PS exposure groups, where Salmotruta were kept in 10 milligrams per liter concentration of PS, separately for each PS particle size that were 0.02, 0.2, and 2 micrometers. The next HCQ exposure group used this drug concentrations of 20 grams per liter for embryons and 0.3125 grams per liter for larvae. And the co-exposure groups of PS with HCQ, PS plus HCQ, used 10 milligrams per liter concentrations of PS, each site separately, and HCQ at the same concentration as in only HCQ groups. And the effects were examined with confocal fluorescence microscopy and 3D reconstruction. And so confocal imaging of live Salmotruta embryos and larvae revealed that the presence of HCQ enhances plastic accumulation. The PS fluorescence is marked in red, and we can see that in the second row of PS plus HCQ exposure, the PS accumulation is noticeably higher than in the first row where Salmotruta was exposed to only PS particles. The 3D reconstruction revealed PS particle, here shown in red color, accumulation on the surface of Salmotruta embryos. The accumulation of PS particles on the chorion was found to be affected by both the particle size and the presence of HCQ. Particles of size 0.2 micrometers covered a larger area of the embryo surface. And in embryos treated with PS plus HCQ, the PS particles were found to be covered by the embryo chorion mucus, which explains why the fluorescence signal seemed weaker. And confocal imaging performed on histological specimens revealed body tissue erosion, yolk sac resorption disorders, and spinal curvature in the larvae after exposure to ACQ and smaller size PS particles, both alone and in combination. In the HCQ exposed group on the left, the abundance of the malformations increased in a concentration-dependent manner. And finally, what we notice is that HCQ and PS with ACQ tended to decrease Salmonella embryo and larvae heart rate compared to the control group, specifically over longer exposure period of 96 hours. In addition, compared to the control group, gale ventilation frequency significantly increased in larvae after 24 hours of exposure to HCQ or PS plus HCQ, but remarkably decreased after 96 hours period, except of the group affected with the 2 micrometers sized PS with ACQ. And to conclude our findings, we observed that the presence of HCQ enhances plastic accumulation in Salmonella embryos and larvae. ACQ severely affected Salmonella development in a concentration-dependent manner, causing body tissue erosion. And interestingly, the abundance of developmental disorders was lower in PS plus HCQ exposure groups compared to only HCQ groups. Also, HCQ and PS with ACQ co-treatment tended to significantly affect Salmonella embryo and larvae heart rate and larva gill ventilation frequency compared to the control group, specifically over longer exposure period of 96 hours. Smaller size PS particles also tended to have a greater impact to these functions, and it highlights the importance of the duration of the exposure to pollutants and the size of PS in ecotoxicity to aquatic animals. And so our findings underscore the necessity of environmental risk assessment when dealing with mixtures of contaminants, and additional research focusing on molecular and biochemical endpoints is strongly encouraged. And thank you very much.
I am very happy that you come back to Lithuania, and I think we will continue a collaboration together with Dr. Živilė Jurkelienė, and I wish you the best in your scientific career. So, thank you again. And we have next presentation. Dr. Van Lufti Van Johari from Malaysia, from Putra University. I think he is.
Hi.
Yes, yes, I can see you. It is very nice to see you again. Also, we have a lot of meeting with Van Lufti Van Johari discussing, and he is also participating very active in our research, writing project, publications, participating in conference. And I just have a small information after Dr. Van Lufti presentation. We will have a discussion about sampling and sample preparation and some analytical problems. We are planning to have this scientific research in Malaysia, and I'm asking to stay until the end, and maybe your scientific knowledge will be useful for us, and maybe in future we will have a very big research group and about microplastic problem in the world. So thank you again, and I'm inviting to present your scientific results.
All right. Hello, everyone. My name is Wan Lutfi Wan Johari. I'm actually very new in this field. So basically, this is not from my study, but what I'm planning to do with my student on the microplastic project. So so what we're trying to do is try to explore the relationship between microplastic and water quality parameters or index. So again, as introduction, I probably won't go a lot on this or on the microplastic itself, but I will more on the water quality parameters. So Southeast Asia is a major plastic pollution source, and Malaysia faces a data gap on microplastic in rivers. So we don't really have a lot of um, data, okay, or baseline data on the rivers, maybe like 1 or 2 for now. So if we're doing it in Mersing in the future, maybe it's the third one. I mean the third or the fourth. So it's still pretty new in Malaysia context. And basically microplastic is less than 5 millimeters the size, and river always act as the transport pathway to the ocean, and water quality actually reflects the actual aquatic ecosystem health and public safety. So in Malaysia, we have the water quality index that being used to check the status of the river. So whether it's good for recreation or used for drinking purposes and so on. Okay. Rivers in Southeast Asia transport major amounts of land-based plastic to oceans due to poor waste management infrastructure. So studies have indicated that the occurrence of microplastic can be attributed to specific anthropogenic waste on land, such as cosmetic products, okay, washing clothes, because some of our clothes has fibers in it, plastic fiber, and recreational activities. Okay, people put their waste in the trash can, but it all eventually end up in the river and so on. Significant positive correlation found between microplastic abundance and parameters and water quality parameters. And this is a study by Sarkar et al. In India. So we actually have one in Malaysia that did the study, and I will talk about that later. So what is Malaysian Water Quality Index? So there are many water quality index in the world, and Malaysia is one of them. So in this index, there are 6 parameters that being measured, and when they measured, okay, they will be used in calculation. And when they do the calculation, they will get the index, and they will say, okay, whether it's in class 1, 2, 3, 4, or 5. So class 1 is a very good cleanest level of water. So it can be used for conservation, water supply, and so on. So class 1, 2, and 3 can be used for water supply. And usually in Malaysia, the river is almost class 3. Okay, so it still can be used for drinking water purposes, but it need to be treated. Class 1 usually at the upstream of the river, and it can be used for conservation and fishery and so on. Okay, and if it's more than 3, usually it's used for irrigation, and if it's class 5, cannot be used at all. So this is just the calculation, and it's kind of like regression or something like that being added into the quality index. And when we calculate that, then we will compare or correlate with the microplastic abundance and so on. Okay, and usually when we do the measurement, okay, it's pretty simple, and usually this measurement is being done by not really technical person. Anybody can go into the river. I mean, especially people who works in government agency, they can go and take the measurement, and they do routinely on rivers in Malaysia. So they will do DO, dissolved oxygen, pH, turbidity, suspended solid, ammoniacal nitrogen, COD, okay, chemical oxygen demand, BOD, and many others. Okay, so I just put some of this here, and these are using standard method that being approved worldwide. So basically, there are many methods of measuring this, and usually in order to measure the quality index, we measured using standard methods. Okay, water and wastewater standard method, like the book is really thick, this thick, and usually people will use that to measure water quality parameters. There are many water quality parameters for rivers, but there are selected few that being measured routinely, and because it's very easy and so on, and it's used in the calculation. As you can see, the water quality index is being used, only 6 parameters are being used in the calculation. So about the microplastic, there are currently not so many paper. Maybe I miss out few papers, but here is in 2 studies. Okay, one is in Selangor River Basin, which is in the area of more north to the Selangor state. Selangor state is a state where our capital city located. Okay, I mean, we have capital city Kuala Lumpur in the area of the Selangor state. So Selangor River and Langat River, the one at the bottom here, are both in Selangor. Okay, Kelantan is pretty much in the another state that has a less dense population compared to in Selangor. Okay, so these two and the one that is closer to the to Malaysian to the capital Kuala Lumpur is the Langat River. So as you can see here, Langat River has more particles, mean abundance particles per liter, which is 1464 particles per liter due to the urbanization. And here in Selangor River, even though it's in the state of Selangor, but it's much less population because it's a little bit far away from the capital city. So Kelantan River, even though it's in the less dense population, however, it's it go through a major city as well in the Kelantan. Okay, so all of these 3 rivers were classed as class 3, and they found out that okay, in Selangor River is 1.44 particles per liter. In Kelantan is a little bit higher, and in Langat River it's 1400 here there. So and in Langat River usually has okay, maybe I accidentally copy paste wrongly here, but this one is in Kelantan River, and Langat River has much less dissolved oxygen. Okay, I have to check again, but I copied the wrong here. But over here, it's due to the urbanization, industrial activities, and Kelantan it's due to the agriculture and domestic affluents. And we would like to find the correlation between microplastic and water quality parameters. And there are many parameters here. So when we planning to go to Mersing later next month, so some of we will do the 6 parameters for the water quality index, plus other things such as salinity, conductivity, turbidity, and all these can be done in situ and very simple and quick. The thing is that why we want to see the correlation here, because sometimes in order for regular government people to do the measurement, or people in DOE, okay, Department of Environment, people who work there, they want to do the measurement. Usually they are not very technical person. They are just like a regular person who got regular person who go and do the measurement and go back home. Okay, so they don't want to do a lot of scientific and technical stuff. And usually when we do the measurement in the river, and it's like one river, you have many sampling points. So it's really hard. Let's say in one river you have 20 or 30 sampling points, and if you have like 100 or 200 rivers, and that's really hard to do. Okay, so in order to find the correlation between microplastic and all these water quality parameters, are that so that we can link somehow some of the parameters here to the abundance of the microplastic. So when we have for certain rivers, like how many microplastic compared, and have the baseline data, then it's easier for these workers to deduce the amount of microplastic based on the water quality parameters that they easily measured. Okay, because some of these measurement are very quick and very fast, so and easy to do. So that's why it is important to have this correlation, even though this is kind of like not really a very good correlation somehow. But let's say, okay, if we get some ranges in the relationship, then it would be great to have that at least. So in Langat River, of course, suspended solids had a moderate positive correlation, and this is kind of like 65% correlation between suspended solid and microplastic. So nonetheless, okay, people still need to do again in order to get a better statistic on the data. And Kelantan River, okay, shows turbidity, which is also measurement of suspended solid in other way, showed a moderate positive correlation as well. So temperature and had a negative correlation in Langat River. So I'm not sure the physics of this or the chemistry of this yet. However, it is interesting to see whether there is a interaction between temperature and the abundance of the microplastic. Some other parameters are very weak or no direct effect on microplastics. So maybe or maybe not, such as conductivity. Small particles could have negative charge. So I'm not sure about the microplastic, it could even if it's too small, maybe it has the charge that could affect the conductivity. And microplastic mainly influenced by salinity, okay, and suspended solid contributing up to 56%, and this is from the multiple linear regression study. So they did that as well. Nonetheless, it would be interesting to see the mechanism of this salinity, pH, ammonia, and so on. Okay, because suspended solid it's very straightforward. I mean, all the solids that being suspended, you know, that suspend in the water. For example, here Langat River is 65% of it is microplastics. And this is the correlation analysis. And of course, further study, I mean, this is just one study. Maybe we need to do a lot more study. And this is not being done by my me or but another people's project. And as you can see here, turbidity affect the microplastics. Okay, of course. However, it's not really consistent between these two rivers. Okay, and microplastic here, and this is suspended solid, but over here suspended solid is not really correlated. So it's really hard. I mean, maybe much more detail, much more careful experiment need to be done, because it's kind of weird to see that turbidity has some effect, but suspended solid here doesn't have any effect at all. So maybe more because sometimes when you take the in way of water quality measurement, okay, sometimes they take different sample for water quality and different sample for measurement of water of microplastic. So I don't know. I mean, those are the things that could affect the measurement and the analysis. And here is the study by Sarkar, and it shows that they did treatment on the water, and after each treatment, they found that the reduction of microplastic, and also has the effect. I mean, not the effect. I mean, like they found the after each treatment, there is a reduction of microplastic, but also reduction in other things such as phosphate and nitrate, nitrogen, or ammonium nitrogen here. However, in my opinion, it could be the removal is concurrent with the removal of total phosphate and nitrogen. I mean, if they did coagulation or flocculation, of course it will remove the turbidity and microplastic, but it also will remove the phosphate and nitrate or nitrogen due to the chemical interaction with the coagulant. But of course, these need to be done. More study need to be done, and so on. Okay, so a very short summary. Suspended solids and turbidity show positive correlation with microplastic percentage of microplastic to and it's interesting to note the percentages of microplastic to suspended solid and turbidity, and other parameters that should be explored: salinity, conductivity, pH, ammonium nitrogen, and phosphates. All right, thank you. I would like to thank all the people involved here. Thank you, Prof. Reda, for inviting us to give talk here. Thank you, the microplastic team from Malaysia, head by Dr. Rashidi. And that's all.
For your presentation. And we have the last presenter. So now we will start discussion about microplastic sampling, sample preparation and analysis. So some methodology we will share between us, and especially I want to participate and moderate this part. Dr. Rashide. Rashide, are you here?
Yes, I'm here.
Yes, and I want also invite Dr. Sajjad Abbasi. Sajjad, are you here? Yes, I see Sajjad.
Yeah, I'm here.
Also, Professor Simas Shakirzanovas, he is online. I know Greta is in Ireland, and she can speak because I have contact. And Professor Ian Skovan is still online. Professor, are you hearing me?
I'm still with you. Well done.
Yes,
Really
because
nice to hear everyone.
okay. And other participants as Dr. Živilė and other Arūnas Balčiūnas is also from Marine Research Institute, Klaipėda University, because also he participated in our project with his PhD student Victoria Sabaliauskaitė. Also, she did sampling, sample preparation and analysis. So maybe we can start a discussion about microplastic sampling, sample preparation and analysis. And Rashide, please start your discussion. And I'm also asking Sajjad Abbasi to be active in this discussion, because we have a lot of questions, and I think it will be useful for everybody, this discussion.
Maybe we should call as well Noriza and Lutfi, because
Okay.
some of the methodology
Yes,
are
of
also
course.
reflecting to them as part of this sampling properties experiment. I tried to access my file on the methodology. Unfortunately, my software still doesn't allow me to access, because they changed my restriction on the drawing of the methodology. Unfortunately, I tried many times since yesterday, and they give me different access this morning to the different account, and it cannot be transferable. But I would like just to show maybe in a quick figure here. So we were planning on this direction. Can you see my screen now?
Yes, I see, but it is loading some files, but now I can see.
Yeah, but yeah, unfortunately, all my drawings should be there, and I lost access to the account. Yeah, so I would like to ask more detail to the teams here, if you would like to help me, especially on the sampling protocol. And I can't do anything at much, but we already drew all this protocol here, and we even have the workflow as well. But again, we have to. I don't have access, but we can discuss. What I would like to mention to you is we will go for the river sampling in Mersing next month. Is located in the freshwater system. We have almost 10 sampling sites. We have the equipment such as plankton net. Okay, we also have the boats. We also have the flow meter to measure the volume of the sample for the samplings, every single sampling sites. So I believe at the end of the process, we will characterize the polymer, the synthetic polymer, and determine the size. And finally, they will determine the concentration of numbers of microplastic per volume, okay, of the projects. Okay, so my biggest question is we have problem and we do not have experience, especially after we collected the 1 liter sample from the plankton net. Of course, we can do the collection, but of course, we never done anything after the 1 liter collection sample. So as you can see here, we try to avoid some contamination. We will wash, we will make sure that the labels are properly assigned. We will keep inside a storage before we can bring to the sampling site. Now, I would like to ask you in a conventional way or in a modern way. Probably Prof. Cowan can discuss about the modern way, and maybe somebody else can also talk about the traditional way. How we can do sample prep easily or rapidly before we can do spectroscopy analysis. I think spectroscopy analysis is not our concern because we have expert in many part of the collaboration. But now, shall we discuss whether we can do partnership in sending the right sample to your laboratory, and let's go for open discussion for everyone. Let's we do for the classical way. Anyone would like to start first? How is the classical way to filter microplastic? And of course, sizes also dependent on this IR and Raman measurement. I don't think so that we worry about the Raman and IR because the submicron analysis can be done with Squawan easily. But now we just make sure that we get the right amount of analytes. We will probably be challenged about the QA and QC, and let's discuss. Anyone would like to give opinion, or they would like to share some advices on their own
So
protocol?
Rashidi, if I understand you correctly, you're pretty clear on how you're going to collect the samples in situ, yeah?
Yep, up to 1 liter storage.
Yeah, and then how would you transport those back to the lab?
Yep, and from the laboratory to your spectrometer.
And
that's the
and it's in the lab. We're focusing on what that process is.
Yep.
I see Aruna has his hand up.
Sure, Aruna, would you like to share something that you can share on the screen that we can learn from you?
No, I have not prepared anything to put on the screen, but firstly, thank you for all the presentations and information which was said today. I think it covered the full spectrum of the microplastics and nanoplastics analysis and so on. But going into your research and into your objective, first thing I see needed is to make a clear definition what size fraction are you focusing on. And this will be determined initially by the mesh size of your net.
Yep, that's right. Sorry,
I did not see the mesh size on your scheme. So this is first of all, and then from the size category, you can go into the later, let's say, choosing either a Raman or a FTIR or both analysis to help, let's say, improve the cost effectiveness. Then secondly, I did not see a control or a sample pollution blind sampling schemes in any actually presentations today. So this factor of everyone mentions that it's highly risky to be sample contamination is a very important thing, but I strongly suggest showing that you will do the control and in which way you will do the control, either putting a parallel blind sample along the full sampling procedure or doing the blind samples with the blind sample procedure, or following with a parallel clean sample and then later looking at it to eliminate the contamination.
So we have some plans based on the previous discussion with our team. So the first one is we would love to collect the environmental condition of the boats, for example, the type of paint in the boat, maybe as well with our clothes condition. So we try to avoid any unwanted polymers that probably visible to our naked eyes. And the last one is, yes, we will make sure that we will wash the whole nets before each trolling system. So that's what we can do during the sampling protocol. In the lab itself, of course, our lab is not really equipped with the high-end system. We have filtered water system, but it's not on the micron level or sub-micron level, since we just have normal filter water that we have on. It's not, our lab is not dedicated for a microplastic project, because our lab is just a general lab. And of course, what we can do is we can make sure that our apparatus are clean, dry, and at least store in one condition before the sample prep. Okay. Alternatively, we also can bring the sample to Bangkok for another clean laboratory dedicated for microplastic. But again, to transport 1 liter times 10 bottle is around almost it's a huge volume to transport, and we would like to avoid that protocol. So I believe that in a classical way, a lot of benchtop experiment, but maybe in a modern way, I do not know. Could be we have some new solution in market. We just dip one substrate maybe, and then we can measure polymer, a very specific or maybe robust system. But again, we will not be able to see how much is actually the quantity of the microplastic, because we will not dip like 100 of substrate into the to the solution. But what I can learn as well, yeah, we can do the filtrations. That's what we can try our best to the right filter size. And of course, when we know the right dimension of the particle, then we will mesh to the right spectrometers that we can use. And I don't think so that we will use OPTIR in the current project. We may start using ATR and Raman. Yes, somebody will also use our sample for their own objective from France. So they will love to use our sample without any sample treatment. So I assume what they need from us is, once we got the 1 liter sample, it's very likely that we will send 50 ml of filtered sample to their lab, because they would like to see the interaction of microplastic with the biological component, because they said they don't want to have any chemical treatment in the sample prep. So imagine we have 1 liter jar, then we will split that sample to France for the OPTR, and they will do their own filtration system lah, which need for the OPTR need, because they don't want to have big sample. But when it comes to our Raman section now, we don't really worry about the ATR. And Raman needs something small, so I need to get ready with the right amount of filtration system. Plus, how many filter setup that I need to apply for 1 liter jar sample? That's a question to the floor. Because at the end, somebody even mentioned to me that they will only even analyze 1/3 of the filter. They only will analyze 1/3 of sample on the filtered paper, right? Instead of the whole filtered paper on the whole sample. I mean, sample versus population. Let's open the floor.
All right.
So Rashidi, if I'm sorry, you go, Sajja.
No. Let's go ahead.
Yeah, so there's emerging a number of commercial products for filtration, some of which are quite expensive, based on laser preparation of specific pore sizes, etc. And coupled with that, there's also numbers of products out there allowing for low background, particularly for Raman FTIR studies. Most people will use some established vacuum filtration processes, and I think there's still not a standardization of what filter beds should be used with that. There are a number of protocols, European-based protocols, I think, for microplastic evaluation, maybe an ASTM as well, that would be good to consult. But obviously we have to appreciate that not everybody can operate and process in a clean room environment. So, as I say, while there is good practice, defining good practice is the important thing, rather than conforming to an established international protocol, because they're very varied at this stage.
If I may
Is that
add,
Yeah.
Rashid, it's still a bit unclear. Will you do the trolling, initial trolling, using some sort of a manta type net?
Yep, that's right.
So then the mesh size is going to be around 300 microns.
Yes, that's right. We have we already have the net in Malaysia. So we should be able to collect anything larger than 300 micron for this work. But of course, we will control the size between 5 millimeter up down to 300 micron.
Yeah, then it's
And 5 millimeter.
completely how to say, unnecessary to go into a certain analysis if you go with such a large fraction. I mean, why you want to use such a sophisticated methods as Raman or other? You can just use ATR for such a large particles to identify the bond.
Yeah, that's okay. So if you see the composition of the team, we have different laboratory where they have different setup. Of course, our lab or even our partners lab in different part of Asia, they only have ATR.
Yeah,
So anything that larger than 1 millimeter or between 1 millimeter and 5 millimeter, we can analyze easily lah. That's pretty sure first one. But when it comes to anything below than 1 millimeter down to 400 micron, of course they are suitable for different techniques. So that's the reason why I'm asking here. So on the same sample, we will divide them into maybe two major category of pathway. One is 1 millimeter above or between 1 millimeter to 5 millimeter fraction, and another one is below 1 millimeter to 400 micron. So, but of course, we don't want to abuse the Raman laser just to measure 1 millimeter particle, isn't it? It's not make sense to measure 1 millimeter using Raman.
Yeah, that's completely clear to me. I just wanted to follow up on the second part of the question, is that if I understood it correctly, then you're gonna do also the bulk sampling of the water itself in let's say 1 liter jars.
1 liter jar will be bring to the lab, and we will start to do the filtration using the normal sieve, the stainless steel sieve. That's our first approach. Also, we were told by our partner we can collect or harvest the one that we can see on visible eye. I think 1 millimeter should be enough, isn't it? And even we don't need to use density separation method at this moment, because the water itself can float the fragments, and we can harvest the plastic. But when it comes to the one that cannot be seen on the naked eye, now I would like to ask your opinions. How we pretty sure that we collect plastic, and of course all the time we will need to perform degradation analysis, I will call it oxidation first, maybe with the hydrogen peroxide first. We can decompose some of the organic materials before we can collect the smaller fragment of plastic. Or shall we start first with the sample treatment before we can do the filtration. So I need your advice how it's much more strategized. Prof. Kawan, normally we work on raw substance on your cases. You don't normally work on the treated sample, as far as I'm concerned. And normally, even in your spectroscopy work, you did not perform any work on the spectral processing, because once we introduce one experiment, we're going to lose some property.
Yeah, so when we previously ran this as a sort of commercial service for various different companies, and the standard approach that we then used was I'm trying to find the protocol, but was the standardized pre-treatment in terms of filtration, treatment with peroxide to reduce the organic contamination, and then collect from there. We used to in those cases then have a 10 centimeter filter bed, which we would do a rapid scan with optical microscopy, and then through a coordinate system identify where the sites of interest, firstly for FTIR and subsequently for Raman, would be located. But yeah, and then in terms of once you have the spectra, it needs a degree of interpretation. Databases always look very attractive when you put the sample in and out pops the answer at 70%, 80%, 90%, whatever. I do remember a colleague of ours who was not a chemist, unfortunately, who said, "Oh, we've got two different types of plastic here. We've got polyamide and nylon." So, we need to just use a degree of
quality index,
interpretation there, and then it's very difficult to be objective in terms of the spectroscopic identification. But that said, again, the image processing software, we used to use ImageJ, and ImageJ's got great procedures for adjusting background contrasts and identifying outlines of particles, and then does the shape and size analysis on that basis. And that actually was the bulk of what we did there, rather than too much FTIR and Raman.
Right. I welcome to the floor as well to give some advices, especially on the lack of apparatus in our lab in Malaysia, and sample treatment needed to be done after the sampling. I don't say that it's a small windows of time, but yeah, we're working on the tight line of system, because we have daily routines. So I would assume normally people will treat one sample per day at the most that it can do, isn't it? When we come to the liquid sample, during the sample prep in the laboratory. So how's your practice in your lab? Can you do more than 2 liters of sample per day, or how is your capacity to do the sample prep normally in your laboratory routines for the microplastic sample prep? Because I've seen in other part of the world, they normally can do even only a maximum of 2 sample treatment per day. It's not due to the strong protocol. And of course, the strong protocol also produces a backlog of sample. And anyone would like to share some advices, chemical treatment versus non-chemical treatments? Of course, the non-chemical treatment is great for people who would like to study the interaction between the biological component and microplastic. That's what they requested to me. So I will send around 50 ml of the concentrated sample to their laboratory. But again, the same sample itself need to be analyzed to be make sure that we remove all the unwanted organic material, isn't it? So because we don't want to have misclassification, we don't want to abuse the laser, we don't want to abuse our time because too much inorganic material, too much carbohydrate from the trees, too much bird feathers. That's what we aware lah in river. And also in Southeast Asia, Dr. Lutfi also can comment about the surface sampling. If we have issue with the soil, Dr. Lutfi, we should also comment how we can eliminate what do you call it, floated particulate in freshwater system, because this river is not like a clean, super clean water in Tioman Island. It's muddy. And we will collect almost muddy sample as well in the jar, and come with a few. I mean, the large particle can be eliminated easily, isn't it? I think during the sampling, we will chuck out the small trees or whatever levers. We will remove that one easily lah. But when it comes to the muddy environment, Dr. Lutfi, how do you comment, and how do you expect some interference from this muddy environment? Because he also doing this work in the environment of freshwater system. Or even if you, Arunas or Sajat, in your previous background, did you measure anything on muddy environment?
We measured wastewater treatment plants. We measure
Wastewater treatment.
Curonian Lagoon, which is highly affected by eutrophication. So in the samples we have a high amount of organic material during the warm season. And we definitely encounter in cases when we have let's say 5 or even more centimeters of organic material on the filter.
Okay,
so
sure.
Clogging of the filter itself.
Yep.
So these situations are all familiar, and we try to solve them various way, either dissolving organic material itself fully. Then it takes time. Then it takes even more time than 1 sample per day, which you mentioned.
Yep, that's true. That's what we try to expect.
And then it's very time consuming, and it's again, you have to make some sort of compromises in certain ways.
So it will be time consuming that we expect.
Then we focus on the larger fraction of the particles. We try to search, and then we use aeration and filtration, using aeration of the samples to get rid of the organic material.
Okay.
What would you mention that you have this muddy composition of the water and a lot of organic and inorganic material? Then I don't see how can you escape density separation in your sample treatment.
Yes, density separation. So it's a must lah. So we will do that
by
one.
Density separation. Then, if you focus on the salt solution, then you are initially saying that you will not get certain polymers because they will sink as inorganic material itself. Then you by using salt is what 1.2 moles per liter. So if you have to use a different let's say solution for density separation. We have polyvolframate, I think, in the laboratory, but it's not used oftenly. We try to stick to this common way of density separation using salt, the saturated salt solution. But then we declare that we cannot find let's say higher density particles simply to the fact that we cannot extract them from the initial sample itself.
Makes sense. So like, why don't we avoid density we just avoid the saturated sodium chloride, for example. We just use the water itself that we use during the initial process of sampling. Okay, the water is still there. We still can see them floating. Am I right? It's still a concept of density separation.
If it's a large particle, then there's no problem, and then you can almost manually collect it.
Yep. Okay.
But we are talking now about the microplastics and in the range of 300 to 1 millimeter.
Okay, sure.
Which your net will be 300. Mesh size is going to be 300. So you will, on the paper, you should not get smaller fraction particles in your sample, unless it's clogged by the organic material and you get the full range of water what you get. But then, yeah, it's going to be difficult to declare the size fraction itself in the results. But let's stick to that. You use 300 microns as a manta net. You get whatever is above 300.
That's right.
And this 300, using a visual analysis,
impossible.
In such a high density of organics, it's not reasonable. You have to separate somehow. Then in other cases, when we have these high quantities of algae, in our case, in the samples, we use subsamples. So we take 5 different portions of the sample. Smaller ones. We calculate how many microplastics we have in each of the subsamples, and then we have a mean amount for the whole sample.
Okay, makes sense. I agree your point. Okay. I think there's another strategy after we found out what happened to our sample from Mersing. We do not know. Maybe it was raining a day before. It could anything happen. It could be like maybe there's a storm from the ocean, so everything pulled into the river. But we will sample the sample in the middle of the river lah. So we will try to avoid the bank side, and the net will be in the middle of the on our right side of the ship, isn't it? So yeah, but again, the clot or the waste, or could be anything. That will be the sample treatment part lah. I accept your point. And we expect some challenge.
Can I add to that?
Yeah, Lutfi.
I think it depends on where and how you sample the water, because for example, if you move the boat, it will if the river is shallow, then it will bring the mud to I mean I'm not sure because I haven't been to Mersing River, so but if it's moving towards the ocean, then it could be not as shallow. So if it's too shallow, then when the boat move, it will have circulation on the banks,
the propeller, I would say,
on the sediment at the bottom. So when you do sampling, sometimes maybe you need to stop the boat just in case. I'm not sure. Maybe we can talk to the boatman. It depends. And usually, like stop the boat and then try to move somehow. Wait for a while before we take the sample. So maybe that's one of the way to do that.
I'll follow your advice as well, but I believe we will do the trolling. We cannot stop the process because the flow meter will measure the volume of the water going to the net, because there will be some calculation involved with that one, according to the definition of the concentration of the volume. So volume is there, it's almost constant across the measurement after we made the consistent measurement or protocol. But when it comes to the microplastic, now we need to know. We don't want to overestimate. Of course, we will not do overestimated of microplastic. We will do underestimated of microplastic lah, because our limitation of the setup of the sample prep. Yeah, we do not know. Any more further advice from the people of the floor? I also have some syringe or some filter like 0.2 micron, but it's even smaller than the one that we have during the our protocol. We limit to 400 micron, so there's no point that we go for anything below 400, because we only capture anything that larger than 400 micron. So when you go to the lab, there's no point that we use filters smaller than that region. Am I right, people from the floor? So we should focus filter that larger than 400 micron in the lab lah.
Sorry, I have a general point. As you told, you wanna microplastics larger than 100 micrometer. So
400.
Yeah, 100 micrometer. Yes, more than this.
Yeah, but the net is 400. The threshold is 400 size.
400.
400. The net is 400 micron.
So how you can get the microplastics lower than 400 micrometer? Because you are using the net with pore size of 400 micrometer.
Yep.
I'm here correctly, because you can find a net with pore size of 30 micrometer. I'm
yeah,
wondering
we already received the 400 micron net. I'm sorry, I have to mention that our instrument or our logistic has arrived, so we are using 400 micron net.
Okay, so if you want to focus on lower microplastics, it's really hard, because I'm working on microplastics size down to 1 micrometer with micro Raman and micro FTIR here. It's really hard, really difficult. But if you want, we can speak about. But for your target, more than 100, I think it's really easy. Just need to get your samples, and after washing the all of captured material in the net, in the glass jar, and transfer to the laboratory, and you can use hydrogen peroxide 30%, for removing all of material.
Absolutely.
And also sometimes you couldn't remove all of material. On that case, we use a 10% KOH. That is really strong. And then we can see that if really need density separation or not. Because if we use density separation, we increase uncertainty, and during the density separation, we maybe unwanted pollution or contamination enter in our sample. So you can see that your samples need really density separation or not. If need, you can use zinc chloride. We use it because it's really suitable for extracting microplastics. And then I think your main equipment for detecting microplastics is really visually, and you can confirm them with Raman and also FTIR. So if I heard correctly, you told me that you don't have any visual equipment or not?
Yeah, in our lab, we do not have any. We do have microscope, but I think it's not really going to be helpful to look on the sample at this moment, especially on the huge matrix component. I'm really more have worry more towards how we will be able even to collect the microplastic and store it on the surface of substrate, for example. So I assume our project, we will send the sample to foreign country outside Malaysia. We will need to transport the microplastic as well. Where we should put the microplastic that after the collection, and whether they need to be really super dry or they just need to be in a wet condition, because we will transport the sample to foreign country. And how do we store the collected microplastic? Because I've seen some people who transfer the particle manually to the sticker paper, for example. So the microplastic stuck on the surface of on the surface of sticker paper. So it's like a double-sided sticker paper. So they just transfer particle they found and onto the surface. So then, of course, it is good if this just within bench to bench. But now we're looking between Malaysia to Europe countries. So it's also the method of transportation to different countries as well. It's not just collecting, but storage. So I would like to ask advices from people around the world who always have partnerships in collaborations. So how we transport materials, or how we transport microplastic.
I can, it's really challenging because I had this problem also, but maybe we can use some blank samples to be sure that how many microplastics lost or added in our samples.
Okay.
But I can suggest that filter your samples on Teflon filter, and Teflon filter, can be used in future for, after when you have Teflon filter, you can add some Nile red. So Nile red can absorb to filter and background, and we have a lower interference because I think Nile red can be absorbed in the filter, and we can also absorb on the microplastics, and we can use this fluorescence microscopy for detecting microplastics. However, these have a little uncertainty for finer microplastics, but for bigger microplastics, it's suitable that we use it in our laboratory. So, but I'm agree that the sending or transporting samples is really challenging. But I can just suggest that we have a positive and negative control samples when you want to send samples in European countries.
Sure, positive and control. Yep, sure. Scowen, would you like to add some more what you think that you will advise before you accept the sample through the from the point of the courier? Of course, we will do the courier part, but of course, it's a long journey from Asia to Europe.
Sure.
The sample can be dry upon the delivery.
I'm sure many colleagues will have seen it, but I put a link in the chat.
Okay,
to an inter-laboratory EU project where it's in drinking water, but it's quite useful because it gives you a little bit of a view on where the EU directives may go on microplastic determination. Anyway, I don't think anybody's got a cut and dried method for doing this. So everyone's saying all the right things. I think as part of the study, you just got to make a choice. Now, what you could do is subsample the liquid and send that to the laboratories. Yeah, so you fractionate the liquid and send people 100 mils or so, and then you'll not only get the comparison of their
results
analysis, but also there's sample prep, and actually it's the sample prep that's the I guess the big variable that goes on here.
It's true.
So that might be one avenue. Of course, it's going to be tricky, but putting it into some clean glassware and then transporting it is not impossible. It's expensive, but not impossible. The other approach would be you do the sample prep in your lab in Malaysia, including the filtration, and then send people the filter beds to have a look at.
Yep.
Now that means that all the sampling process is common, and that may not give you such diversity in the study. I don't know what other colleagues feel, but to be honest with you, I know this. I shouldn't say this as a chemist, but the analysis bit is actually relatively straightforward. Some people will use the optical method, some people will use thermal methods, some people will use the spec methods, but there's not a lot of variation there. Could be useful for training one another, but it's the sample collection and particularly preparation that I think is the thing that you probably need to make some decisions on.
Yep. I see your point. Challenge transporting sample across continent. That's another things I should consider. We can have the sample, we know the protocol, we have the right locations, but at the end, I have to make choice on the sample preps or the untreated samples, and of course, that we are open for collaboration. Especially, I'm heading to France next October.
Sure.
To Toulouse. So that's one of the
But
way.
I think whatever thing that you do, that point that Arun has introduced around, you know, some sort of control is really important, because the what's the best word? The
Quality assurance.
the samples journey, for want of a better term, you know, is fraught with unknowns, particularly if you're sending it by courier or transport methods, whatever. So, you know, you just got to make some decisions, I think.
Mm-hmm. So our work on the solid state experiment was pretty easy, because they dry, they are stored in individual particle. We don't have contaminations between sample. We even have their lot numbers for every particles, and we managed to have 100 of particle and spectra, and we did the works last time on solid state lah. But the one I say is,
but the other important thing, Rashidi, is to just work out what questions are you trying to answer.
Yep, what the research question.
Okay.
All right, sure. Professor is here back. I'll give back the floor to you.
Yes, I think we will continue a discussion about our project, and I want maybe to thank for everybody for participating in this conference and discussion. Also, I want to say that in future, in October or in November, we will organize the second conference, and we will present results which we will get during this project, which was supported by Lithuanian Research Council. Project number is MIP 23139, and we are doing research on atmospheric-riverine flux in transport and the impact of microplastic and microrubbers as heavy metal specters on the Curonian Lagoon. And thank you for everybody, and see you again in the next conference and next meetings. Thank you. Bye-bye.